Okay guys, so this is Hitesh Tripathi, and in this video we are going to see what is topological sorting in directed graphs and plus what is KAHN's algorithm. Okay, KAHN's algorithm is also for topological sorting. Okay, so firstly let me tell you what is topological sorting. Topological sorting is arranging nodes in such an order that every node which is traversed first or such that you have two nodes u and v, and there is some path from u to v. Okay, then in your order u comes first and then comes v. Okay, so in Hindi I will say that कि कोई एक नोड है जिसके पहले तुम जितने भी नोड्स ट्रैवर्स कर रहे हो, ठीक है, वो सारे नोड्स उस ऑर्डर में जो तुम्हारा एक नोड है उससे पहले आए. ठीक है, तो फॉर एग्जांपल यू कैन से दैट right now you are learning React. Okay, for React you must be knowing HTML, CSS and JavaScript. So if you arrange order of these texts, then your order will be HTML, then CSS, then JavaScript, then React. Okay, so this will be your order. Okay, so in this way you can also check for graphs. Let's say you have a graph which is 1. Okay, now this is 2. From this, let's say this is 3. Now let's say this is 4. And let's say this is 5. Okay, now if you will see in this graph, you are in node 5. Okay, or you have to learn fifth process. Okay, before that you must be knowing process 3. Okay, and for knowing process 3 you must be knowing process 1. Okay, so if we make order of these, then it will be something like this. Okay, for 5 you must be knowing 3, for 3 you must be knowing 1. Okay, now if you will check for 4, you must be knowing 2, and for 2 you must be knowing 1. Okay, so we can place 4 here or 4 here also. Okay, let's say we place 4 here. Okay, and for 4 you must be knowing 2, so you can obviously you have to place 2 before 4. Okay, it doesn't matter you place 2 here, okay, here or here, in according to 4, in relation with 4. Okay, let's say we place 2 here. Okay, now all nodes are in this order, so you can say that this order is topological sorted order, in which every parent node, you can say every parent node appears before its children. Okay, fine. Now one observation from this, there are some observations, let me quickly show you that. Okay, one observation from this order you can check is, for a single graph there can be more than one topological sorted order. How you can say that is, for 5 you were having some order 1, 3 and 5. Okay, main condition is 1 and 3 should be before 5. Okay, now for 4 you must be having 2 and 1 before 4. Okay, but there is no relation between 4 and 5, so in this order we have put it 4 before 5. We can put 4 after 5 also. Okay, and before 4 you have to place 2, so you place 2 here, and before 2 you have to place 1, so you placed 1 before 2. So it can also be a order of topological sort, and you can clearly see that this order and this order are different. Okay, so by this you can say that there can be more than one topological sorted order for a single graph. Great, one observation is checked. Second observation is, your graph can't contain cycle in this. Okay, just make a simple observation. Let's say you have a graph which have cycle in that. Okay, 1, 2, then this is 3, and again. Now this is a cycle. Okay, now let's again brute forcefully make topological sort order. Okay, for 3 you can say you must be knowing 2. For 3 you must be knowing 2. For 2 you must be knowing 1. Okay, for 1 you must be knowing 3, which is a contradiction. You can't place 3 before 1. Okay, because 3 is already placed. So you can easily see that for a cyclic graph you can't sort nodes in topological order. So these are the two observations. One is your graph can contain more than one topological sort order, and second, your graph should be acyclic directed graph. Okay, fine. Now how you will find this topological order? So for this you have two methods. Okay, you can use BFS also and you can use DFS also. So by using DFS, this will simply be called KAHN's algorithm, and we will see it later in this video only. Firstly, let's see simple implementation using DFS. Okay, DFS. For DFS, firstly we will obviously be having a visited array. Okay, this is our visited array. Okay, and second thing we will be having is, you can say, a stack. Okay, let's say this is a stack which will contain our topological sort order. Okay, you can perform DFS from any node. Okay, let's choose any node and let's say that is 1. Okay, you started DFS from 1, then you will traverse its adjacency list and you will go to 2, then you will come to 4. Okay, then you will come to 4. After 4 you will see that there are no more childs of 4. Okay, so you will place 4 here. Okay, and obviously you will mark all these nodes visited, 1, 2, 4, all are visited. Now why I placed 4 in the stack? Because after 4 will be in the end of your topological sorted order. Why? Because after 4 there are no more childs of 4. Okay, so you can easily say that कि 4 किसी के लिए भी essential नहीं है. ठीक है, 4 is not essential for any process, or 4 is not essential for any other node. Okay, so that's why you placed 4 here. Okay, now you go back to 2 and you will see that 2 is also no more essential for any other node. Okay, 2 is also no more essential for any other node. Okay, or you can say that 2 has no more unvisited nodes, so you can place 2 here. Okay, and 2 is already visited. Fine, then you will go back to 1 and you will see simply that 1 has childs. Okay, so you can't place it in a stack, and again you will go to 3. Now in 3 you will see 2 childs, 4 is already visited, we will not do any action, and you will come to 5. Okay, we will make 3 visited also, and 1 is already visited. Okay, now you will come to 5. Now in 5 you will again see that there are no more childs of 5. Okay, so there 5 is not essential for anyone. Okay, so you will place 5 in a stack. Okay, and make 5 visited. Okay, now 5 has no more children. Go back to 3. 3 also has no more children which are unvisited. 4 is already visited, 3 is already visited. Then you can simply place it in a stack. Okay. Now you will get back to 1, and 1 also has no more children left which are unvisited. Okay. So you will simply place 1 in a stack. Now all the nodes are visited. Okay. And or you can also say that your stack size is already n, total number of nodes. So you can say that you get one topological sorting order. Okay. And which is 1, 3, 5, 2 and 4. If you noticed before, this is completely different from that order we have brute forcefully made. Okay, so again you can see that more than one topological sorted order can exist. Okay, and you simply get this topological sorted order. Now this was simple DFS implementation. Okay, fine. Now for that you can see the code. Okay. So this is CP algorithms. Okay, you can visit this site and check the code. In this code, they do not use stack, they simply use vector and reverse that vector at last. Okay, so you can use a stack here for that, and simply you will go for 1 to n in every node, and whenever you will get any untraversed node, you will call DFS. Okay, and at last of every DFS you will push that node in your vector whenever you will have no unvisited nodes in adjacency list of V. Okay, now let's see simply KAHN's algorithm. What is KAHN's algorithm? Okay, sorry guys, this is taking some time, or we can make some new graph also. Okay, now we will see here what is KAHN's algorithm. We are doing it by BFS. So for BFS you can simply observe what we do is we traverse an adjacency list of single node fully. Okay, then we go to some other node. Let's say firstly let me draw the graph. Okay, this is our graph. Okay, now what does KAHN's algorithm say? That firstly take out all nodes which have in degree 0. What do you know by in degree? Number of incoming edges, simply. Okay, number of incoming edges are known as in degree of a node. Okay, so we have to find out all the nodes which have in degree 0. So obviously for all the nodes to count in degrees, we will take a array. Okay, let's say in degree array. Okay, in this we will mark in degrees of every node: 1, 2, 3, 4, 5. Okay, simply cut that. Okay, now we have to mark in degrees of every node. Okay, so how we will do that is simply when we will be taking input of this graph, let's say there is a edge between 1 and 2. There is a edge between 1 and 2. Okay, this is a edge, then simply in degree of 2 will be incremented by 1. Okay, so in degree of 2 right now is 1, in degree of 3 is also 1, in degree of 5 is also 1. In degree of 4 is 2 and in degree of 1 is 0. Now you have in degree of 1 0. What does this means? Simply observe that if in degree of 1 is 0, then there are no essential process that should be done before 1. This is the main observation. Why we are finding every time in degree 0 nodes is because we will place all nodes in the answer array. Okay, I am saying कि क्या करोगे तुम लोग, क्या कर रहे हो कि हर बार इन डिग्री 0 वाले नोड्स ढूंढ रहे हो, ठीक है। तो इन डिग्री 0 का मतलब क्या कि उसके पहले तुम्हें कोई भी नोड्स एसेंशियल नहीं है जो ट्रैवर्स होने चाहिए, ठीक है। तो सिंपली व्हाट यू कैन डू इज प्लेस दीज नोड्स इन योर आंसर एरे एट स्टार्टिंग and then you will check other nodes. Okay, so in first traversal you will get in degree 0 node 1. What you can simply do is take an answer vector. Okay, this is our answer vector. In degree of 1 is 0. Place 1 in your answer vector at a starting, and main thing is remove all the edges from 1. Because why we removed all these edges? Because answer is already placed in node 1 is already placed in our answer. Okay, now 1 will be not counted as essential node for 2 and 3 because we have already placed that. Okay, now you will again update your in degree array because you have removed some edges. So you will remove 2 and 3 1 1. Okay, you will decrease 2 and 3 by 1, so it will become 0 and it will also become 0. So new in degree array will be something like this: 0 0 0 4 का 2 and 5 का 1. Now you will again 1 is already visited. Now 2, this is 2 and this is 3. You have to place these two in your answer. Okay, place 2 and 3 in your answer and simply remove edges from 2 and 3. Okay, this edge will be removed and from 3 this edge also will get removed. Now in degree array will be updated and it will simply become 0 and 0. Now what you have to simply do is place 4 and 5 in your array. Okay, now answer vector sizes is equals to number of nodes. It means that you got order of topological sorting. Now you can again see observation that in one action you got 2 nodes which have in degree 0. It means you can either place 5 before 4 or you can either place 4 before 5. It simply means that 4 and 5 are independent of each other. Okay, so order of 4 and 5 doesn't matter in topological sorted array. It simply means that there are possibility of more than one topological sorted order. Okay, fine. So this was simple implementation of KAHN's algorithm, okay, which we have discussed right now. In this we are simply using a array in which we will count number of in degrees, and for BFS implementation we will simply take a cube. Okay, so try to make a code of KAHN's algorithm by yourself. Still, if you have any doubt, tell me. I will place the code in comment section. Okay, and you can find there. And if you like this video, give a thumbs up in this video and share this video to your friends whoever wants to learn topological sorting. Okay. Last observation is why DFS implementation is better than KAHN's algorithm is after placing all nodes in your answer array, you have to check again what are in degree nodes which have in degree 0. Okay, so obviously इसका कोई मेथड तो है नहीं, ठीक है, तो तुम्हें क्या करना पड़ेगा, पूरा ट्रैवर्स करना पड़ेगा सारे n नोड्स में एंड अगेन यू हैव टू फाइंड आउट इन डिग्री 0 नोड्स. तो ऑब्वियसली इतने से तुम समझ गए होगे क्यों बेटर है KAHN's एल्गोरिथम से DFS ज्यादा फॉर टोपोलॉजिकल सॉर्टिंग. और you can implement it by using priority queue. Okay, so simply check that, and if you have any doubt you can ask in comment section. Thank you guys for watching this video. Ask your doubts in comment section. Thank you guys.